ammeter. So ammeter, suppose there is a circuit, say there is a resistance and battery is connected like this, and we want to know what is the current flowing in the circuit. We connect an ammeter in series with the circuit. So this will show how much current is flowing in this circuit. So for this the ammeter is used. Therefore it is a current, ammeter is a current measuring instrument in any circuit. So it is connected in series in the circuit. First point about this ammeter. So from galvanometer only we get a ammeter. We do some modification of the galvanometer to get the ammeter as well as voltmeter. First let us see, this is the galvanometer. G, this is a galvanometer having a resistance galvanometer where it will G is equal to galvanometer resistance. So here the confusion comes. We connect here to make this galvanometer as an ammeter. We shunt, that is we connect here a small resistance in parallel, that we call it as a shunt resistance. S is equal to shunt resistance. See here here we are connecting a shunt resistance in parallel, and that thing is connected. This is called, total thing is called ammeter, that is connected in series. Always a confusion. How to avoid the confusion? You must have seen in the TV or camera, that is something like PAL, VHS, exactly. I also do not know what is this, but you will find this. Here in India you have to use in this mode, here in this mode. We don't need this. We don't need this. We need this one. This is voltmeter. This is high resistance, and this is series. We use this statement. For same thing for ammeter. For in place of voltmeter, ammeter, high resistance, low resistance, in series, in parallel. That means for ammeter, a low resistance, it should be connected in parallel. It means a low resistance called shunt resistance is connected in parallel to convert this galvanometer into ammeter. This is the arrangement for ammeter. A and B, it means these and these are in parallel. It means voltage across this point and this point are same, since both are in parallel. Remember this one here, a shunt resistance here, low resistance is connected in parallel, and this arrangement is connected in series. This and this will confuse even for the voltmeter. So now we'll finish up. It means this galvanometer, this is the galvanometer shunt resistance. Now this galvanometer is converted into what? It is converted into ammeter. Now the current through this, see now the current IG, what is I? I is equal to full scale, here we get two full scale reading, full scale current of ammeter. Whereas IG, what is IG? IG is equal to full scale current in galvanometer. Two things here we have to remember. If I is flowing, then only this ammeter will show full scale, because the ammeter will be like this and it will from 0 to full scale reading, say about 2 ampere, in between 1 ampere. To show full scale reading from here to here, this need I, this I is required. And for the galvanometer, see, for the galvanometer, for full scale reading, we need Ig, full scale current of galvanometer. This is full scale I, capital I is equal to full scale, to get a full scale diffraction in the ammeter. So this is the difference. So the potential across this is point A and point B. This potential, what is this potential? This is equal to current. Potential means what? Potential means potential difference. Potential difference is equal to voltage into current. Here what is voltage? Voltage V into V is equal to I into R. Here far between this path. So PD across the galvanometer is equal to current through this. See here the current, full scale current will flow. Here what is the current? I minus Ig will flow here, because by Kirchhoff law Ig will go here, I minus Ig will go. What is this current? The current through this one into resistance, that is galvanometer resistance. Also the potential difference between these 2 points, this point, both are same, which is equal to what is I minus Ig into what is the resistance, shunt resistance S. It means both are equal, because both are equal. It means we can say we have to find out the shunt resistance. So we write I minus Ig into S is equal to Ig into G. Ig into G. By getting, okay. Now we can write I into S minus Ig, or we can easily go for S. What is S? S is equal to Ig by I minus Ig into G. This is the value of shunt resistance, which is this. We have to select a suitable resistance. It should be low resistance, ALP, that is low resistance connected in parallel to convert the galvanometer into ammeter. So this is the value of low resistance which is shunted across the galvanometer to make it as a ammeter. So it means this whole thing, ammeter can be described first a galvanometer with a resistance G, and this is shunted. A shunt resistance is connected here, and this arrangement is called ammeter. And the value of the shunt resistance is given by this expression. We use ammeter for measuring current through a circuit. See, suppose this is a circuit, resistance, and we connect an ammeter here, and this is a voltage source. See, voltage source, and this is the resistance. So current will flow like this. This ammeter will show how much current is flowing. But in actual case, some current is flowing. Suppose when we don't connect this one, what is the current? The current is equal to the true value of current. True current is equal to I is equal to total voltage applied divided by its resistance. The current, which we call it as I, the current read by ammeter is I dash, and I dash will always less than I, because the measured value of current will always be less than the true current. Suppose when we connect an ammeter here. Why? Why? Because see, as it is now, I is equal to V bar. This is the equation for the current through the circuit, that is true value of current. But here ammeter, see ammeter connection already we have seen. Here ammeter means this is the galvanometer. A shunt resistor is connected in parallel. So net resistance, see resistance of ammeter is equal to galvanometer resistance G is in parallel with the shunt resistance, that is in total parallel GS by G plus S. So where RE is equal to ammeter resistance. So we can draw the circuit like this. This is the original R and this is the voltage, this one, and this ammeter, this can be represented like this with a galvanometer and a shunt resistance. This is nothing but the ammeter. The ammeter is replaced because this is the ammeter is replaced, and further this can be replaced. And its resistance, what is its resistance? Its RE is equal to GS by G plus S, where G is equal to galvanometer resistance and S is equal to shunt resistance in ammeter. Shunt resistor in ammeter, because both are in parallel. For parallel connection we can write, or this we can measure like this. You can write this is ammeter, this is E. Now the current is here high. Now current will be I dash. Why? Because one more resistance, that is resistance due to ammeter, is added here along with this one. This is V. This is added now. In that case, now the I dash is equal to V. I dash is equal to V divided by this resistance R plus resistance due to ammeter. Resistance due to ammeter, R I dash, we can write it as, or we can write I dash is equal to V divided by R into R plus, what is this RA? As it is, RA is equal to, this is the value of RA. It means I dash, certainly I dash is equal to V into R plus RA, and I is equal to V divided by R. It shows I dash is less than I. Less than I. So it means what we'll do, see, in ideal condition, we have to see ideal condition what happens. See, in ideal condition, to make I dash is equal to I dash is equal to I dash is equal to I means what? This is the extra vector. This should be made as 0. Then it will become V by R. Then in that case, RA should be equal to 0. In that case, I dash is equal to I. Because when RA is equal to 0, E is equal to 0, I dash will become V by R if this is equal to 0, which is equal to I. It means what? The ammeter resistance should be equal to 0 if this is the true value of the current, when without ammeter this is the real value of current, but when ammeter is connected the current will be less. That is why the reading of ammeter is always less than the actual current in the circuit. For an ideal ammeter, its resistance should be 0. What do you mean by ideal resistance? For an ideal resistance, as it is, we have seen, if RA is equal to 0, I is equal to I dash. It means the ammeter resistance should be 0. In that case, I is equal to I dash. It means I is equal to I dash for ideal condition. For ideal ammeter, I is equal to I dash. This implies ammeter resistance is equal to 0. That it clearly says for an ideal ammeter, its resistance should be 0. Then only these questions always come. For ideal voltmeter, its voltmeter resistance should be infinite. For an ideal ammeter, its resistance, that is ammeter resistance, should be 0. These questions have come several times.